Hi, now we're going to proceed to talk about each individual acid derivatives, starting from acid chloride down to amides. Your book kind of goes over all the nomenclature in 21.6 and then all the mechanisms basically lumped together in 21.7. And reading through that, I found it a little overwhelming and confusing to me to try to do everything all at once. But I think it gives a good perspective at the end. So what I recommend is I'm going to go over each individual nomenclature and mechanisms for each acid derivatives. But at the end, what I'd like you to do is take a step back and read through 21.6 and 21.7 more carefully to get a bird's eye view on these four acid derivatives, because there's a lot of common theme throughout it. And I think once you get that, even though it seems like a lot of individual reactions, is a very easy chemistry to learn. All right. So we'll start with acid derivative, acid chloride. We're going to start with the nomenclature, and it's very simple for a lot of these, which is that you're going to look at all these acid derivatives as derivative of carboxylic acid. So you're going to look for, so for example, the parent carboxylic acid with the benzene with the acetyl OH, which the chlorine is the derivative of. So you would name the acid, drop the ic acid, and the add YL chloride. Okay, so for example, this would be the parent, in which you would name that benzoic acid, but it's not a carboxylic acid, it's an acid chloride. So it's benzoyl chloride. And then you name the substituents as you would normally name, which is, in this case, this is a isobutyl group, and it's in a para position, so it would be para isobutyl benzoyl chloride. So that would be the full name for that compound. And you should also be able to obviously recognize that you have acid chloride when you look at the name. So hexenoyl chloride, you would make hexane would be 6 carbon long. So you would draw the 6 carbon 1, 2, 3, 4, 5 chain, and then notice that obviously all acid derivatives has to be at the end. So you could choose either end is acid chloride, and that will get carbon 1, so carbon 2 at carbon 3, notice the ene, so you put the double bond at carbon 3, and notice once again acid chloride is understood to be in carbon 1, so you don't need a numbering for that. And then you have on the 4th carbon a methyl group. Alright, and then if you fill in all this with the appropriate number of hydrogens, you have the correct structure for 4-methyl-3-hexanoyl chloride. All right. So next thing that you need to know is how would you prepare acid chlorides? You haven't had this before. And this is pretty useful reaction because acid chlorides are so reactive. A lot of times we do prepare this in lab so that you can react with a nucleophile, and is a very, very quick reaction. All right, so the overall reaction is that we're going to take a carboxylic acid and we're going to react with something called thionyl chloride, which is SOCl2. And with that, you're going to convert. So thionyl chloride is SOCl2. And you're going to convert that into the acid chloride. All right, so that's the overall reaction, and this is the reagent that you need. All right, so this is a mechanism that is shown here, and this is the same one as in your book, and I just want to briefly go over the mechanism of how the acid chloride is made from the carboxylic acid. So let me just zoom in. And so we have a carboxylic acid, and notice the thionyl chloride, SOCl2. Think about how reactive this reagent would be with two chlorines attached to the sulfur. So obviously, one of the first things that's going to happen is a nucleophilic attack to that sulfur, and it does the same kind of chemistry that you've seen before. So you make a bond between the sulfur and the oxygen, so you put a dash there, and you have a negative charge on that oxygen because we broke the double bond. All right, obviously this is an intermediate. This oxygen should have a plus charge, right? So then the chlorine is, you have two chlorines that it's going to be readily leaving. So the O minus comes down and makes the one of the chlorines leave, and you have this intermediate with the plus charge on the oxygen, and then you have a chlorine that has left. Now that chlorine negative ion is going to serve as your nucleophile and attack the C-double O and break open the double bond. So you have this intermediate where it's single bonded here. You made a bond between carbon and the chlorine. And what happens then is the O minus comes down, as you've seen before. And then you basically make this a leaving group. All right, and which is a good leaving group. So then you make the acid chloride, which is the product that you wanted, and then you have this byproduct, which is the leaving group, and the leaving group is not a stable compound, and as soon as it forms the HCl, and then the sulfur dioxide, which is a gas, and that bubbles out of the solution, pushing this equilibrium to the right, and that's the byproduct of the thionyl chloride. All right, so this is how the carboxylic acid will be transformed into acid chloride. All right, so once you know how to make the acid chloride, what kind of reactions can you do with them? As you know, as we went over before, there are tons of nucleophiles that are available to do the normal nucleophilic reactions. So overall would be you have acid chloride plus some kind of nucleophile. Now the nucleophile could be obviously outright negatively charged, or it could be a weak nucleophile with a hydrogen attached. So many of the examples that you're going to see are nucleophiles, weak nucleophile, because acid chlorides are so reactive that anything will react. All right, so you have C-double-O and then Nu, which means that the byproduct is HCl. All right, now HCl, because it's acidic, it may actually cause problems with the rest of your molecule that might have an acid sensitive group on it. So a lot of times when the reaction is run, it is run in presence of, so reaction run in presence of a base, and the base usually is a pyridine, which has this structure. So it's a very mild base, and its job is to basically react with the HCl. To form this pyridinium chloride salt, which is not acidic anymore compared to HCl. So its job in running the reaction in presence of pyridine is that it just soaks up the HCl, and the HCl has chem. react with anything else in your starting material. All right. So I'm not going to write out all the reactions, but basically, if you go to the next page, I copied and pasted all the different nucleophiles that you could have. So notice the making of the acid chloride with thionyl chloride. But you could go back. So one of the first nucleophile that you should be able to figure out is water. So acid chlorides are very reactive, so it's prone to hydrolysis. So even if you buy acid chlorides in a jar, you have to make sure that you cap it carefully and that you don't leave it open, because even though moisture in air will react with acid chlorides immediately. So, but if you wanted to hydrolyze it, so this will be a hydrolysis reaction. And notice the pyridine in these reactions in the presence of, so when the HCl is formed, it reacts with the pyridine. All right, so water, the nucleophile will be OH replacing the Cl, and the extra H will go with the Cl, making HCl, which reacts with pyridine. All right. And by the way, you should be able to draw mechanisms of these reactions. So let's go over alcohol as well, because they'll be very similar in the mechanism. So when you have an alcohol, same thing. You're replacing the OR with the Cl, and then H will go with the Cl, making HCl. Okay. So just so that you know how to draw the mechanism, so you start with the acid chloride, and let's say you're doing a hydrolysis, then this is going to go and react right, and then this is going to come down and make the chlorine leave, so you almost have the product. And then all you need is a proton. So chloride minus is the byproduct, and either the water, most likely, is going to come and grab the extra proton. So you form the hydronium ion again, and then you have the Cl minus as the counter anion. So if it was a alcohol, you would start with OR group here, and then the mechanism will be exactly the same. So you would have tetrahedral intermediate, and then you have to have the chlorine leave. Remember the addition and then the elimination. So here's the addition part, and then here's the elimination part, and then the hydrogen transfer will happen to give the final neutral product. Okay. So I'm not going to go over all the nucleophiles, but you're going to have nucleophile with water, you have nucleophile with alcohol, you have nucleophiles with amines. Those are the nucleophiles that you're going to be responsible for. So notice here you have ammonia, primary amine, secondary amine. So all these three are doing the same thing. Basically, the nitrogen source is replacing the Cl. And then notice the excess, or it has to have at least two equivalents. And the reason for that is one equivalent is used for as a nucleophile, but the second equivalent, instead of using pyridine when you're reacting with the amines, the second equivalent is serving the purpose of pyridine in reacting with the HCl. All right, so that's the important thing to keep in mind, that you need at least two equivalents when you're reacting with the basic amine.